Yeah,
Yeah,
recording is
recording
started.
is started. Oh, thank you so much. Fine. So what I
Fantastic.
will do is, can you permit me to share my screen?
Yep, I
Yep,
will do
I
that.
will do that. Yeah.
Um, so participant,
Participant.
just a second.
You have to stop sharing probably.
Oh, I have to
Oh,
stop sharing.
stop
Okay,
sharing.
okay, done. Go
Okay.
ahead.
Yeah, thank you. Very good evening, all gentlemen. And This is Gokhale. Unfortunately, I could not be present with you guys last week. So today we are going to do some very specific topics as mentioned. So before I get on to that, permit me to share my screen. Okay, I think my screen is now up. And so let's me get started with the topics for today. So today we are going to these two.
Gokhale, are you there?
Hello, can you hear me?
Yeah, sure.
Yeah,
Go
sure.
ahead.
Go ahead. Okay, because I'm just putting up
Mm,
my share. Yeah, can you
yeah,
hear me now?
yes.
Yes. Good. Okay. So today what we are going to talk about is primarily we are going to introduce ourselves to the concept of developing a few algorithms, and the starter to this entire concept per se happens to be a quick study of what we call as a Deutsch algorithm, and this is essentially a special case of Deutsch Joshua's algorithm. So we're going to discuss that also, and then we will see how that can be sort of simply implemented in Quiskit. And at the same time, I'm also going to talk about what exactly is the concept of a quantum oracle. And if time permits, I'm going to just get on to the discussion of how we can construct the quantum oracle also, and show a very quick demo on IBM Quiskit, right? This is like the beginning of how to develop algorithms, I should say, the baby steps into how to develop algorithms, right? Maybe this could be the starting point wherein we use these concepts to get on to more serious algorithms for both communication as well as compute. So let us first understand what is this Deutsch algorithm. So it is not a complete algorithm per se, but it is identified as a subset or a subproblem of the Deutsch-Joshua algorithm, right? So we'll understand what that Deutsch algorithm or Deutsch-Joshua algorithm is. But at the outset, let me tell you to the fact that if at all the same algorithm is implemented in a classical manner, like using your classical computing mechanisms, vis-a-vis implementing that in quantum mechanisms, you typically tend to attain a massive speed up, right? So what do you mean by this massive speed up? Uh, the general algorithm, which is Joshua algorithm as it is called, it typically tries to complete your entire operations essentially in one computation itself, whereas classically it might take 2 raised to the power of n plus 1 computations. And this 2 raised to the power of n plus 1 computations is typically for data size of n bits or n qubits, right? So this is where you say, okay, I can straight away get that sort of a speed up. And the Deutsch algorithm is a special case of this Joshua algorithm, wherein we typically tend to set n equals to 1. In that particular case, it still gives you a speed up of the orders of 2, right? So if you just look at the Deutsch algorithm per se, it will give you a speed up of 2. What do you mean by speed up of 2? As Prakash just now mentioned, whenever we have an algorithm, we always normally try to measure what is called the time complexity, right? And that is identified with the big O notation, as we call it, right? Given the size of the problem, how much time do I have to spend in order to solve the problem? And more specifically, as the size of the problem increases linearly, does the time also increase linearly? If that is the case, then I say I have got a linear time dependency, or linear, what do you call it, as a complexity. Whereas there are a lot of cases where, as the size of the problem increases linearly, the time required to solve these problems might increase exponentially, right? So these are non-linear time complexities. So these typically tend to what are called as non-polynomial times and stuff like that. And that is where quantum algorithms tend to be more handy. Right? So let us understand these aspects as we move forward and discussing several of these algorithms. For each of the algorithms per se now onwards, we'll be talking about what type of a speed up I can typically tend to achieve. So what is this Deutsch algorithm? Right. So let us understand that first. Imagine you have got some sort of a black box or some sort of a magic box. You really do not know what exactly has gone in out there. Some sort of a mystery box is there. We call this as an oracle. And this oracle provides you some sort of a mapping. And what is that sort of a mapping? It typically takes an input, right, which is input essentially as a binary value that could be representing some state of the system, and we identify this input as a description over n bits, right? So I can now say that the input is an n bit string made up of zeros and ones. So 0 and 1 is now called as an alphabet, so the binary alphabet. And this n out over here, the input part, indicates the fact that okay, you're going to have a string of n occurrences. And if this is given to the oracle will give an output which is a single bit, which is either a 0 or a 1. And it will typically tell you this outcome 0 or 1 depending upon some sort of a function that is implemented within the oracle. So what is that oracle? Oracle is some sort of a mystery box which performs some sort of a transformation on the input and then generates some output. And the output out over here is either a 0 or a 1, right? So what is this black box? So that you can just have different forms of implementations into the black box, right? So you say that okay, I've got an oracle which I really do not know how it is implemented, but given let's say a set of n bits of zeros and ones, it just computes somehow magically, gives me, let us say, the even parity out of this. So that is typically the outcome of that, and the even parity value could be either a 0 or a 1. So that could be a one type of an oracle. So but we are talking about a slightly different type of an oracle which tries to implement the Deutsch Joshua algorithm. So what is this Deutsch Joshua algorithm? We really do not know how to implement that at this particular point of time, but we know the nature of its working. So what is the meaning of this nature of the working? Given any input, a string of zeros and ones of a particular size defined by the parameter n, the Deutsch Joshua algorithm tries to find out if the oracle is balanced or constant. Right? So the output is indicating whether the inputs are balanced or constant, or maybe I should not say inputs. The operations which are carried out there will tell me whether it is balanced or constant, right? So what do you mean by balanced? So it will tell me the fact that whatever operations are going on within the oracle will be balanced if, right? Remember, when I talk about an n input bits, right, there could be 2 raised to the power of n different combinations that can occur. For example, if n equals to 3, we can have inputs which could be 0 0 0, 0 0 1, 0 1 0. You know, you have any of these 8 different combinations going all the way up to 1 1 1. So out of these 8 combinations, we could just have any of these combinations pumped in as the input to the oracle. And what my Joshua algorithm tries to tell me is, if this particular operation being carried out, if the function is balanced, then half of the outputs are 0 for the inputs that are subjected, and the other half are 1. So which means what? If there are 8 input combinations, for 4 of these input combinations, the output would be a 0, and for the remaining 4, the output would be a 1. In such case, I now say that the function implemented within the oracle is said to be a balanced function. Whereas the function implemented in the oracle is said to be a constant function if, regardless of whatever is the input value, the output is all either zeros or all either ones. So which means to say the fact that, okay, my oracle is implementing a function where the output is constant irrespective of the input, and the constant could be either a constant 0 or a constant 1. So my Deutsch Joshua algorithm tries to tell me whether the function that is implemented is balanced or constant, right? So this is essentially the crux of the so-called Deutsch Joshua algorithm, right? Why do we need this? We will just defer this for the next session. So next time when we typically do some crypt algorithms or other type of algorithms, we will try to use these fundamental concepts out over there. So here is a small example of, let us say, some sort of a function. So someone defines a function, and that function could be something like this. My function is take any input A and it performs a classical AND operation. So this dot is just nothing but the classical AND operation, and that classical AND operation is with a value equal to 0. And when I have anything ANDed with 0, obviously I know the fact that the output would be 0. And this is said to be a class as an example of a constant function. So what do I mean by this? If at all I talk about once again n equals to 3, I will now say that the 3 inputs are x2, x1 and x0, and my function operates on these 3 inputs x2, x1, x0, and the actual computation will be x2 dot x1 dot x0 dot 0, right? So please understand this. Now whatever the inputs that are given, I perform an classical AND operation along with 0, and that always gives me a 0 as an output. So which also means to say the fact that my Deutsch algorithm will tell me the fact that this is a constant function because the so-called oracle is implementing some function where the output is always equal to 0. You're getting the point? So this is essentially one simple way of trying to identify how a constant function might look like as part of the oracle's implementation, right? So this is a simple example. Let us take another example here, the second example. We talk about, let us say, the oracle implementing a function which is an XOR function, right? That plus sign out over here indicates the XOR, the classical XOR. And here, once again, I have got 3 input bits, x2, x1 and x0, obviously giving rise to 8 different combinations. And my function is x2 XORed with x1, XORed with x0. So basically, whatever the inputs, they are internally exclusive OR, and I get an output. Now, if at all I look at all the 8 combinations over which this function can work out, right? Sorry, this is not, there is a small mistake here. I think I'll correct it right away. Yeah, there is a mistake. It is basically perils of copy paste. Okay, fine. So for n equals to 3, essentially now we have x2, x1 and x0 going across all those 8 combinations. And here what we have is, for the first case of 0, 0, 0, we get an output equal to 0. Second case of 0, 0, 1, we get an output of 1, etc. And these are all the outcomes for 8 possible input cases. And now I see the fact that out of these 8 input cases, for 4 cases, I get an output equal to 1. 4 cases, the output is equal to 0. Which also means the fact that my oracle or this functional implementation in that particular black box is supposed to be a balanced oracle. Right? So this is a simple example of what we mean by a constant oracle or a balanced oracle. Sometimes people call this balanced oracle also as a non-constant oracle as well, non-constant oracle. Okay, so what is this Deutsch algorithm? Deutsch algorithm is a very special case where we set n equals to 1. So what do you mean by n equals to 1? Automatically, this entire problem boils down to the most elementary fundamental mechanism, wherein I talk about my Oracle mapping function taking an input either a 0 or a 1, transforming that to generate some value 0 or a 1. Right? So which also means the fact that I have the inputs of 0 or 1, and my Oracle maps or operates on these inputs 0 or a 1. So what are the outputs? Outputs will be f of 0 or f of 1. What is the f of 0? Whatever is the function is working on the input 0, or the function is working on the input 1. And these are the outputs. So the outputs are f of 0 or f of 1. And my question is, I want to find out whether this outcome is balanced or constant. So what do you mean by constant? Irrespective of the input, if both these two functions f of 0 or f of 1 are producing the same output, either 0 or 1, then I say it is a constant function. If not, if f of 0 is not equal to f of 1, then I say it is a balanced representation. Okay, so the same thing, we have just reduced the entire problem size down to setting n equals to 1, and that is a Deutsch algorithm. So mind you, once again, the output is not the output from the computation. The output is either a 0 or a 1, indicating what is the nature of a computation. You're getting the point. We are talking about what is the nature of a computation, whether the computation is balanced computation or whether it is a constant computation. That is the outcome of this entire black box. That's how we are assessing what is the nature of the computation that is happening within the Oracle, trying to identify whether it is a constant outcome I'm getting or whether it is a balanced outcome I'm getting. So that is the outcome of all this exercise, right? So we are really not talking about what exactly is the actual value, right, operated upon by this black box on the input. We are not talking about that, right? So let us look at the approach, right? The quantum approach. But before we do that, let us very quickly go through the classical approach. Okay. So what is this classical approach? The classical approach typically happens to be a sequential process. So what I need to do is something like this. Let us say I've got a 3-bit use case currently. And what I now need to do is what? For each of these 3-bit use case, I need to provide the input. Start with 0, 0, 0, right? Remember what is the output. Then start with 0, 0, 1. Remember the output, right? This way I keep on doing it, run over all the 8 possible cases, and then analyze my outcomes and then decide whether this oracle is a constant or balanced. You're getting the point? Which means what? My sequential algorithm will have to have some sort of an iterative process which goes through one by one each of the combinations of the inputs and then measures the outputs, right? And if all the outputs are the same, then I know it is a constant function. If all the outputs are not the same, I know it is a non-constant function. More specifically, I have to also have got a counting mechanism to indicate whether both these combinations are giving rise to an equal number of zeros and equal number of ones. In that case, then I say that the system is balanced. Right, so that means what? There's definitely a process which has to be an iterative process, and on a minimum, right, on a minimum, it will have to run through all the combinations. So if it is an n bit input, then I have to run through at least 2 raised to the power of n iterations, right? So that is by sequential approach. So let us look at the same consequential stuff for a Deutsch algorithm. So what do I need for a Deutsch algorithm? Remember, n equals to 1, because of which I'll have to perform only 2 computations to find out the answer. Right? When I perform 2 computations, I perform the first computation on the input bit equals to 0, the second computation on the input bit equal to 1, which means that I'll have to execute the function with input equals to 0, execute the function with input equals to 1. So f of 0 and f of 1 needs to be evaluated. And then I can identify whether both these two outcomes are the same In case I declare it is constant, if they are not the same, then I can declare the fact that this is balanced. You're getting the point? So which also means the fact that I need to perform two computations. Now just notice the fact that to perform one computation, I might require any amount of time. That depends upon the function. If it is an XOR function, it will require so much time. If it is some other function, it might require maybe something like an encryption process is there. It might require probably, let's say, 10 seconds. Or if it's even more complex algorithm that is bumped in out there, it might probably take even about let's say 2 hours or so. That 2 hours is the time that is required for assessing the outcome for one input combination. You're getting the point. So just notice the fact that each computation which we talk about could take any amount of time. So let us say that is t units of time is what I specified. So looking at this entire Deutsch algorithm from a classical point of view, you can now look at the overall behavior by identifying the complete, let's say, state or state-wise behavior, and this can be identified or modeled as 4 different combinations of the way function is getting executed. Okay, so what I can now identify is something like this. There are 2 inputs and 2 outputs, so we can have 4 different combinations, right? So 2 inputs and 2 outputs will give rise to 4 different combinations. So what are these 4 different combinations which you can typically get? So here is a case wherein you have about FA operating on the input 0 could give me a 0, and FA, the same function, working on, let's say, the input 1 will give me a 0. Right? So please now understand, with 2 inputs I'll have 4 possible combinations like 0, 0, 0, 1, 1, 0, that way. So I can now talk in terms of 4 different implementations of the functions. So I have this FA operating on 0, FA operating on 1. Similarly, FB operating on 0 and FB operating on 1. Similarly, FC operating on 0 or FC operating on 1, and FD operating on 0 and FD operating on 1. So these are the 4 possible cases I can have. I cannot just have any other type of a function that is operating with 2 inputs and 2 output bits. Okay, so if you examine these outcomes, what are the possibility is that FA and FD, look at the first function, FA and FD, right? FA and FD typically always produce what is called a constant function. FA produces constant 0, irrespective of the input being 0 or 1. FD, right? FD produces a constant 1, irrespective of the input, whether it is a 0 or a 1. So I have got 2 functions which are possible functions which are producing a constant function, whereas there could be 2 other functions which produce a balanced function. So these are FB and FC are classic examples of the balanced function. So I call them also as a non-constant function. Right? So what do you mean by that? If at all I need to evaluate on all these 4, I need to typically perform these calculations. Right? So let's say I have to perform at least 2 computations, once on 0, once on 1, to determine this. So I need to definitely perform 2 calculations, and each calculation could take, let's say, t units of time. So out over here, I definitely need to work out on 2t units of time. So that is my sequential or classical approach. And the same thing, what I can do is I can achieve a speed up the moment I transform this problem into, let us say, the case of a superposition, right? That can be done using, let us say, quantum representation of the same problem. So let us look at the quantum solution for this. So a quantum solution typically tries to perform these entire operations in parallel. So what it does is it takes all these input combinations in one single go, and in one single shot of t units of time, it performs typically one computation in parallel, and then gives me the solution, right? So automatically it gives me a speed up of the order of 2. Does not just only order of 2. If at all, let's say you have 3 bit information, then obviously you require 2 raised to the power of 3, that is 8 units of time, 8 into t. Whereas when you talk about a quantum solution for that, maybe there could be 8 different representations which are all executed in simultaneous form, right, using this concept of, let's say, superposition or whatever we talk about, right, maybe in entangled states and stuff like that. And the entire outcome can be realized in typically one computational time, which is t units of time. So works out in parallel. So we're going to talk about that also as we move forward. So we're just laying down some foundations as to how we can now think in terms of very, very simple function operations, which essentially implement some form of an algorithm. Yes, please. Okay. Yeah. I'm getting some echo. Uh, am I audible? Am I audible?
Yes, Gokhale, you're audible. I am trying to make sure that
Okay, fine.
it should be clear.
Yeah, I'm getting some echo. That's it. Okay, fine. I'll continue. So that is basically the advantage. So what is this parallel approach? The parallel approach will get us the solution exactly in one computation using quantum parallelism. So what do I do? So this is basically a first step in this algorithm. That is the preparatory step. So the preparatory step is as follows. I am going to create one sort of a quantum oracle. Now this quantum oracle essentially is a unitary gate. So what do you mean by the unitary gate? It will typically perform some computations in such a manner that it is reversible, right? And it is unitary, right? We know about these properties of a quantum gate. Any quantum gate, whatever it is, has to be unitary in nature. Unitary at the same time, it has to be also reversible. And for this, usually you will have a gate which takes n inputs and generates n outputs. So it will always be an n cross n type of a functional representation. We know about that also. So that is a classic representation or a model for any quantum gate. So what we will do is we will first have to create a quantum oracle. And for our example of a Deutsch algorithm, we define a 2-qubit quantum oracle. And the 2-qubit quantum oracle, I can just represent this as UF. And this operates on the inputs. Now the inputs are no longer 0 and 1 as in the classical form. These are essentially just nothing but the qubits. And I will represent them as the basis vectors ket x and ket y, right? And what is this UF likely to do? It will perform some operations in such a manner that it generates the output, which is x, the first one as it is, and the second bit we now will be transformed as follows. So it will take the second input, performs an exclusive OR over whatever is the function that is implemented out over here, right? I really do not know what is the function that is implemented. So this oracle implements some function called as, let us say, f of x, and that particular f of x is typically operated in an exclusive OR manner over the second, right, basis vector, and that will be my output. And obviously, this being a unitary quantum gate, I will be having two outputs. So the outputs will be labeled as MSB and LSB. Okay, so this is my standard notation which we are going to use. The reason I'm putting both these two pictures, as was also put up in a referred textbook, is because of the fact that there are some books which have a representation where this MSB and LSB positions are flipped. Some of them treat them as big Indian, some of them treat as a little Indian, and there is that sort of a confusion all throughout. But we've been using Qiskit, and Qiskit represents this position as the MSB position. So we're going to stick to the same representation. So this notation is what we are going to use. The upper notation is what we are going to use. So once again, I really do not know what that oracle is doing, but what I'm going to do as my quantum oracle representation is, I will take the input base vectors, right? These are basis vectors, and then perform some operation in such a manner that the output will have x, and the second output would be y exclusive or with whatever is the function f of x. You're getting the point. So I give X, and I know this guy is going to perform some computation. It might take 1 minute, 1 second, maybe or 1 hour. I really don't care. But after the t units of time, it is going to give me fx, and that is what I'm going to exclusive or to determine the second bit position. And what I'm going to do further is I'm going to now check out what is the value of this. So I'm going to measure these values to determine whether that particular UF, the oracle gate, is constant or balanced. Okay, so that is a strategy which we are going to approach. So this is my step 0. So here is the way the step 0 or the establishment of my oracle is defined, right? So the representation is something like this. Give me any state vector or give me any classical state representation of the basis vector like xy. I perform this UF on this xy, and the actual representation of would be, it will be get x. After that will be my y exclusive or with function of x. So whatever is the function implemented by that particular oracle. So this could be, let us say, odd parity, or this could be trying to find out how many number of 0 1 combinations are there. There could be any type of a function out there, right? So it could be any function which is operating on the input string. So that is my function. So if you look at this, what happens is the MSB remains unchanged. So this is my most significant bit x, right? That also still remains unchanged. So MSB portion of my computation remains unchanged, and all I am going to look at and observe is the changes to the LSB. So the LSB changes from y, get y, down to a representation which is y exclusive or with fx. And what is this fx? Remember, fx is the computation which is carried out in the oracle, right? So this is my LSB. So just remember this part. So once again, to get this concept little more clearer, here is a small example. Fx, remember, could be anything, right? Could be any implementation, could be evaluating maybe the event parity, could be evaluating how many number of occurrences of, let's say, a particular string pattern is there in the input and stuff like that. So Fx could be your own algorithm for which you are actually implementing the classical solution, and then now we are trying to contemplate in coming up with a quantum solution for that. Okay, so let us assume that I have got some fx as a function, and that is supposed to be a constant function. So let us understand the working of this. So let us say fx is a constant function. And what do you mean by constant function? Irrespective of whatever is the input, the output will always be the same. So here let us assume that the output will be always a 0, right? So remember, we were talking about this FA, right? We were talking about 4 cases: FA, FB, FC, FD. So FA and FD are classic examples of constant functions. FA gives me constant 0, FD gives me constant 1, right? We have seen that, right? So let us assume that now we have some function which is behaving as if it is equal to FA. So how do we represent this? In essentially in the form of understanding what goes into the behavior of the oracle. Please understand this. At this particular point, I still do not know what that oracle function is. I only know some behavioral things. So I know the fact that, okay, given a series of input combinations, I know the output from this function is always 0. So that is a behavioral fact which I know. So that is also, there is only known. I really do not know what exactly is the happenings within the oracle box. So let us say I have got a 2-qubit system, and with 2-qubit system, what will I have? I'll have the basis vectors as 0 0 0 1 1 0 and 1 1, right? So these are the basic 4 different states, and then I can talk in terms of defining the function f. So remember, u is basically any unitary and f is my any arbitrary function. So I represent this as uf. F has to be a subscript though, and the operations could be something like this. So if I take a uf, so uf is operating on, let us say, the basis vector 0 0. Remember, these are 0 0, and I know the 0 0 can be represented as ket 0 ket 0 for the first one and the second input set. So operating on this ket 0, I will get the same thing, like the first ket 0 will be as it is. The second ket 0 will be 0 exclusive or with the function implemented within the Oracle operating on the input 0. Right? This is the input 0. Okay, and this can now be modeled as let us say ket 0, and 0 exclusive or with f of 0 is now just nothing but once again a 0 exclusive or with 0. Okay, why is it 0? Because I have observed the fact that, let us say, my function is constant, so it will give me zeros only as an output. So just notice the fact that the output will be 0 in all the 4 cases. And the moment I see that happen out there, just notice the fact that the outcome will be actually 0 0 or 0 1 or 1 0 and 1 1, which also means the fact that the behavior from the input side to the output side is absolutely the same. So I can now say that, oh yeah, my Oracle function looks like as if it is implemented as an identity function. Now I can just make a guess by looking at this input output behavior, input output, uh, uh, let's say representations, how the inputs are taken, how the outputs are getting generated. If at all I just look at an observation, I can make a quick guess. And my guess is that, okay, it appears as if it is an identity function, that is the magic within the Oracle. Okay, so that is how I can probably make a guess. So what I now need to do is something like this. To come up with a quantum solution, what I have to do is I will first create a superposition state. Okay, the reason I'm going to create a superposition state is I'm going to implement this in a parallel approach rather than going through each of these input combinations in an iterative manner. I will create a quantum parallelism, and that can be done by setting up superposition, or more specifically what I say is I will be actually working in the plus minus states, right, rather than the 0 1 basis vector states, right? So I will typically set up my superposition in such a manner that I migrate myself from the 0 1 state down into my plus minus state. And how do we do that? We know very easily this can be achieved by using the Hadamard transform. Okay, so what we do is I will create the superposition state, and that superposition state can be operated upon the so-called original 0 1 basis states. So that can be done as follows. Like I now talk about plus minus is just nothing but 1 over root 2 of ket 0 ket 1 and 1 over root 2 of ket 0 minus ket 1. So we know about these two representations. So if at all I just work out on these ket 0 plus minus representations, I get this as just nothing but 1/2 of a combination of ket 0 0 minus ket 0 1 plus ket 1 0 minus 1 1. So just remember the fact that this implementation is so very easy. All I have to do is what use maybe the Hadamard gate to get into superposition. So that is a step one. Once I have done that, I will now apply the UF, whatever is the Oracle function. And this Oracle function now will work out on this so-called superposition of the inputs. So this is my superposition states of the inputs, right? This one. And whatever is my Oracle function, my Oracle function will work on that UF. So I can typically pick up my Oracle function UF and then apply it down to ket plus ket minus. And the same ket plus ket minus now looked upon in my ket 0 ket 1 states will be this. So I will just put this up, and then I just mathematically I'm doing some small jugglery out over here, right? Bringing this 1/2 outside and then pushing this UF inside. So I just will work out UF on individual combinations of 0 0 0 1 1 0 and 1 1. And if at all I operate UF on 0 0, this will be the resultant, right? First bit will be the same, second bit will be 0 with exclusive or of f of 0. Similarly, this also will be f of 0. Here I am going to work out on f of 1 and f of 1. right? Simply because the input x is equal to 1. So I just work out on this UF. So this is what I'm going to get. And once again, right, and I work this out, I can now say that f of let's say one exclusive OR with anything. We know the property of an exclusive or the classic exclusive OR get. One exclusive OR with anything will be a complement. It just typically gets a complement form. Similarly, so which also means the fact that if I say one exclusive OR with f of 0, it is as good as saying the fact that this value will be equal to complement of f of 0. Similarly, one exclusive OR with f of 1, it means it is a negation or a complement of f of 1. Right? So this is basically what I am now typically talking about. Still at this point of time, I am not bothered about what is this f of z, f, the function f. But all I now know is this implements this following representation. So it will be 0, f of 0, and with respect to the second parameter is it 0, complement of f of 0. Third term is 1, f of 1. Fourth term is 1 complement of f of 1 with a negation sign. So remember this, wherever the complement is there, that values are negated. Right? So this is what I have got. So this is my step 2. And now what I have to do is I have to do the measurements. Okay, so measurements will also once again typically identify depending upon whether it's a constant function, I have one measurement. If it is a balanced function, I'll have a slightly different type of measurements. So let us understand these two use cases and then see and observe what exactly means by the outcome from a constant function, what means by the outcome from a balanced function. Okay, so I do the measurement. And what is my measurement? If at all this f of x is a constant function, notice the fact that f of 0 will be equal to f of 1. Right? That's a constant function. That means what, irrespective of whatever is the input, the output will always be the same, either a 0 or a 1. Which also means the fact that f of 0 complement, f of 0 bar will also be equal to f of 1 bar. Right? So if at all I just use this approach and then apply it onto my tensor product, which has been factorized, which remember this is what we have done, I just apply these values now. So I'll just f of 0, I'll just use it as it is, and this is f of 0 in a complement form. Similarly, I've got this f of 1, f of 1 is also in a complement form. I just typically substitute this. What I'm doing is I'm just transforming all these parameters into f of 0 representations only, and then I typically sort of juggle around. So this gives me once again ket 0, ket f of 0. This will be once again ket 0, ket f of 0 bar, ket 1, f of 0, minus ket 1, f of 0 bar. So now if you look at this entire expression now is transformed as a representative only on f of zeros. Or you could have also done it on f of 1, that's a different story altogether, but I now have transformed everything in the form of f of zeros. And if at all I just once again analyze this, I now typically get this, I just club them together. So this gives me ket 0, ket 1 operating on f0, and similarly let's say ket 0, ket 1 operating on f0 bar. Okay, so this is just nothing but my, remember this is just nothing but my ket plus, and this is just nothing but ket plus with a minus sign. Okay, so combine them together, I say this is an operation which is ket plus operating on 1 over root 2 of f0 minus f0 complement. So what does this basically mean? So why did we do so much of this juggling around? If it is a constant function, very quickly look at this. This ket plus is remaining unchanged, whereas ket minus changes over to all of this, whatever it is. So I really don't care about all of this. I only look at this most significant bit, and now I know the fact that the most significant bit is remaining unchanged. So I can very simply conclude the fact that, okay, if the function f of x that is implemented within the oracle, at this particular point of time, I really do not know what it is. If that is a constant function, my simple observation is the fact that the MSB remains unchanged. MSB remains unchanged. On similar lines, if it is a balanced function, or if it is a non-constant function, obviously now what does it mean? Once again, I have got f0 and is equal to f1 complement. Similarly, f0 complement is equal to f1. Remember, this is the approach for a balanced, right? So which also means the fact that if f of 0 is equal to 1 and f1 is equal to 0, so these are the two typical cases, right, that are essentially possible. Then I can also identify the fact that if f of 0 is equal to 1, then f of 1 bar will also be equal to f of 0 and vice versa, right? So just taking this, plugging into the same relationship, remember this is the same relationship, I plug it and then juggle around, I will see the fact that this UF working on ket plus ket minus will translate down to ket minus and some other parameter out over here. So what is happening now? If I once again observe the most significant bit, the most significant bit MSB is flipped. Ket plus becomes ket minus. So which means for the fact that if the oracle is non-constant, right, if it is balanced, then MSB is flipped. So which also means the fact that, okay, I set up my quantum circuit and just only measure the MSB. And if this MSB remains unchanged, then I know the fact that, okay, my circuit is, let's say, constant. If the MSB is changing, then I know the fact that this is non-constant. Right? So this is one very simple way by which I can conclude the outcome whether this particular oracle is balanced or not. Remember, I'm still not worried at this particular point of time as what is getting done within the oracle. What is getting done within the oracle is still my F. I'm not really using the output of this, right? So I'm not really worried about what is this value of f of 0 or f of 1. I'm still really not worried at this particular point of time. Okay, so these are basically the three steps which are required to be performed in the Deutsch algorithm. So just notice the fact that my measurements can now be implemented and I can set up this sort of a quantum circuit, and my quantum circuit goes something like this. I'm going to demonstrate this quantum circuit also immediately right now on Qiskit. Okay, so what is my quantum oracle? Implementing the Deutsch algorithm. So it takes this ket plus minus as the input and checks out and keeps this MSB. MSB will be the same as ket plus if it is constant, or it flips this value if it is balanced. That is my Deutsch algorithm. Remember, if it is uh, not balanced, sorry, if it is balanced, that is not constant, then obviously the MSB would have been flipped. So I have my function out over here, right? And then, it will just typically take these two bits, MSB and LSB bits, which I provide as the inputs. And these inputs are now ket plus and ket minus. And this guy generates to me, and I observe my MSB to find out if it is flipped or not flipped. Now remember, what I'm doing is something like this. I'm doing a bunch of measurements. I'm supposed to be doing a bunch of measurements in the plus minus space. And to do that, measurements in plus minus space, what I do is I just transform that using a Hadamard gate, bring down these values down to the 0, 1 space. Right? So it is as good as saying that I measure values in plus minus is actually the same as measuring in 0, 1 space. And typically I can do that by applying the Hadamard gate. So that is the reason why you apply the Hadamard gate at the output, and then try to do the measurements in the 0, 1 states. Okay, so this is the reason why we use the Hadamard gate out over here, and we use the Hadamard gates in the input so as to get into the so-called state of superposition. Okay, so the three-step algorithm would be something like this. Okay, so here I will be having the first step, okay, where I just typically take the input, and the input would be let us say in the 0, 1 basis. I apply the Hadamard, transform them to, let us say, the plus minus basis, apply them to some UF, whatever it is, right? For our example, let us say we consider FA as the input, right, the behavior, and for FA it is supposed to be identity. So knowingly I'm going to use identities out over here. But technically speaking, it could be any function that is implemented out there. You can just plug in any complex function out over there. So because I know the behavior of FA as an identity function, so I'll just use this identity function in the small example. And I will just have the outputs. The outputs typically once again will come up in the plus minus basis, and I want to do the measurement in the 0 1 basis, for which I once again apply the Hadamard gate. And where do I apply? I apply it only on the MSB, because MSB is what I need to monitor and check. So I apply after the Hadamard gate a small measuring, and then I just check out what is the value out there. Okay, so that is my quantum circuit. So the quantum circuit typically looks something like that. I will just quickly show this quantum circuit also to you. And just see here, these are my input, the Hadamard gate, and this I'm using out over here the identity gate, because I'm implementing the FA, the first function. So this, what is this FA? FA will typically be a constant 0. You getting the point? FA is constant 0. FD is my constant 1. FB and FC are typically the balanced type of implementations. So here I'm just using this identity function, right? Identity matrix, or whatever you might call. This is my step 2. So this is the so-called oracle here, the black box. Okay, so I have to implement something for my simulation. So I'm just knowingly implementing this as an identity function. So I know the fact that, okay, this particular black box, the oracle, is constant 0. And at the output, I measure that, and then I will see the fact that the output is indeed equal to 0. On a simulation, if I just fire this on my real machine, I will see the probability counts coming up most often for this 0 0 on a real computer. There could be some small traces of maybe 0.1, 0.01 type of combinations or tries. Remember, I'm just once again going to run this maybe 1024 times. So if for a few of these iterations, maybe it could be producing a false output, right? So this is just nothing but the small type of an error which comes in, and the output state in that would be ket 1 0, right? A real state would be, a correct state would be ket 0 0. So what I will typically try to do before I go on to the next part is, let me just quickly show you the IBMQ implementation of this. Okay, so I will open up my IBMQ platform. I will log in. Give me a minute. Okay. Yeah. Okay. So I've just logged in into my account, and what I will now typically try to do is I'll just get on to setting up my let's say quantum lab, or maybe composer. Maybe I'll show you both the quantum lab, also a very simple Python code for this also. I'll just show that to you quickly. Okay, so here is what I have, right? I've created a new, let us say, a file, a new project, and I just set up two quantum input lines and two classical lines, or rather two quantum inputs and two classical bits. So this is basically a 2 by 2 type of a network, right? So what I'll have to do is set up this entire thing. So I get started with very simple not operator, and as I add the elements, can you see now this probability state representations would also be changing. Right, so the moment I add this out over here, the automatically by initial states will be all ket zeros, remember. So this definitely now becomes ket 1. This is the least significant bit, Q1 is the most significant bit. Kindly remember that. Right, in IBM QCF, Q1 is the most significant bit, Q0 is the least significant bit. And then just to ensure the fact that all these operations are getting done in the form of, let's say, at the same stage, what I will do is I'll just balance this out with a small identity operation out over here as well. Identity is not going to do the changes. And for my editor, instead of doing these edits in left alignment, I'll just use free flow so that I can place these what do you call these operations anywhere on this line. Okay, so it gives me that sort of a freedom. Or else Qiskit automatically tries to compact everything, pushes them all to the left side as much as possible. So by default it would be left aligned. Okay, so that is the thing. And then I will have to uh, right, bring these gates. This is very important. So I bring this. The moment I add that, just understand what is happening. This first input is getting auto superposition. Because it is going auto superposition, now you will see the states as 0, 0 and 0, 1. And then I'll bring the second Adamat gate here. So this is also now going to bring in into superposition. Now you will see this 4 different states, 0, 0, 0, 1, 1, 0, 1, 1. There are 4 different states with typically an equal probability. If you just examine, the probability is about 25%. Okay, so that is because of this. So this actually completes the step number 1. Okay, so what is happening? I have now created essentially plus minus, right, basis vectors in the plus 0 plus 1. Right, so in the 0 1 which I've used out over here, I am now able to create this ket plus and ket minus using this Adamat. So this is my first stage. What is my next stage? Next stage will be my oracle. Okay, so my oracle will be, let us say, I know the fact that, okay, I'm trying to now check out whether the circuit is going to detect a constant 0. And I know for a constant 0, has to be something like f of a, and that f of a can be implemented using the identity function. So this is an identity which I use. Remember, this identity is actually the oracle. So this part is the oracle. This is the second part, step 2. Because it is identity, effectively you don't see any changes out over here in the outcomes. Then I need to go to the third stage wherein I need to do the measurement. Right? So currently these operations are carried out in the plus minus. I now have to bring it into, let's say, 0, 1. And to do that, what I will do is I'll just get the Hadamard here. Okay, get the Hadamard here. And then once again, after having done the Hadamard, I will also now add up a measurement. So I'll just bring this measurement here and do this. Okay, and just give it a minute. Yeah. Right, I can just see that out over here automatically running, and because of this measurement, it has now dropped down to the state 0, 0. Remember, the 0, 0, what is the actual value of interest to me? The MSB. MSB is a 0. MSB is equal to 0 indicates the fact that, remember, this particular input is a constant, or the oracle is constant. If it were a 1, then I know it is balanced. As simple as that. Okay, so what I will do is quickly run the same thing on my let us say a simulator, Quasm simulator. I'm not going to push it down to the system. I can do that also, but before that I just run it onto the simulator. I'm also going to show equivalent Python code for this. Then we'll move to the next part of the session. So I'll just quickly go out over here for my setup, and my setup already has been set up for running on the Quasm simulator. I have all these options available to me. I can just run this on IBM Perth or IBM Lagos or whatever. But at this particular point of time, I've set it up on the Quasm simulator. And I will now just run it on the actual IBM Quasm simulator. Right? Just wait for a second. Yeah, it has completed. The job is completed. Now you see there is a new job result. So I can open this. Okay, and this is the operation which just got executed, and if I click on that, so this is the outcome I'm seeing. So this is the actual outcome on running on the simulator. Similarly, if you fire the job on the actual device you will be seeing maybe 0 0, and you may also be seeing 1 0, one small bar for a 1 0. It's very very small tiny bar for 1 0 that typically will tell you the state of your error. Okay, so what we have done is we have just only tried to find out what exactly is the behavior of this. Okay, so I will also play around with this for a minute before I switch across. So what I'm going to do is something like this. Come over here and okay, let me, maybe I can, okay, that's fine. What I will do is, this is an identity. I know the fact that the identity essentially means the fact that this is for a constant 0. And if you work out on a similar lines for constant 1, remember for constant 1, you essentially get this implementation as a C naught gate, as a C naught gate. So let us see. We will try to remove this and then implement a C naught gate out over here. So let me remove that. I'm just once again removing this part. Oh God. What is happening? Yeah. I'm cutting it off and then I'll just put a simple C naught gate. Very simple. I can just bring in the C naught gate. So this is supposed to be implementing a constant 1. So what will this guy give me? This will always give me 1 as an output. So that is my implementation. And if at all I look at that, I'll just quickly run this. Once again on the IBM Quasm simulator. Okay, yeah, new job result is there. So this new job result, if I look at that, I'll just see once again the output will be equal to 0 0 only, indicating the fact that this is yet another constant implementation for f of x equals to 1. Output will always be equal to 1. You're getting the point? Whereas if at all these were some other box out over here, and if that were implementing, let us say, a balanced output, then I would have got out over here an output that is equal to 1. So this would have been 1 0. So this bar would have been for 1 0. Okay, or probably for 1 1, whatever it is. Okay, we will see that after I complete the next topic out over here. But my point of interest is, let me also show you essentially a similar type of a code. I'm not going to write the code. I've already put up a small code out there. I'm going to share these codes also with you. So let me quickly go to the IBM Quizzkit lab. This is what we have done in the composer. Give me a second, it will just, yeah. I'm going to quantum lab. I'm switching over from composer. I'm going to quantum lab. Okay, fine. So here I have got a bunch of problems which I've already set up here. So I'm just picking up this Deutsch 1, the notebook. I will work on that and quickly explain to you and then execute these small code snippets. So this is the first cell which is automatically done by Python on the notebook. I'm not typically looking at that because these are all standard includes, right? The standard imports as we call it. So here I'm now having the imports from Quizzkit, import IBMQ, basic AER for the simulator, and then I'm also looking at the provider because a little later on I would like to run this job also on the physical device. So I'm trying to identify which of these devices is least busy, which we have seen last time also. So for that I'm going to have this import. Then I'm also importing quantum circuit, classical register, quantum register, and execute. All these things are required to set up and run your quantum circuit. We know about that. And there is also a monitor that I'm interested in, just to bring out what exactly is the way I can monitor and measure and then examine the outputs. So what I'm once again doing is I'm just setting up a quantum register of 2 units, classical register of 2 units, very much similar to what we have discussed. And then I set up the circuit. So my circuit is called as, the object is circuit. So this is my quantum circuit over 2 quantum registers and 2 classical registers. And what I do, remember, I need the exclusive OR. So I just put up this exclusive OR on the, the I just use this uh, exclusive or the inverter. I'm sorry, not the exclusive OR, the inverter on the bit number 1. Okay, so that is what I am doing, and then I create what is called as a barrier. Now this concept of a barrier is just to ensure the fact that segments of these circuits are executed in typically some sort of a synchronized phased manner. So whenever I have got a barrier, execution will happen up to the barrier. So barrier is something like a, I should say, a stepping mechanism in execution of your quantum circuit flow. So you can just set up your barrier. So I just put up one barrier. I'll just show you how the barrier also looks like. And then what I'm doing is I'm just typically adding up that Hadamard gates at the inputs, and this will give me a mechanism wherein I try to create the ket plus and ket minus, right, with the Hadamard gate. So I'm just using this superposition out there, and once again put up another barrier there, right, just to uh, clearly identify each of this particular operation. And then I will have some of my Hadamard operations. Okay, so here is a very simple Oracle function which I'm going to implement. Right, what is my Oracle function I'm just going to implement? I'm just going to have this identity. Right, remember ID stands for the identity. So I'm just bringing in the identity gate on the line 0 as well as on the line 1. So, and I know the identity typically represents a constant function 0. Right, so I implement this is my Oracle function, and after that I have to measure. But when I want to measure, what I do, I will essentially measure in let us say 0 1, and to do that what I'll have to do, I'll have to essentially set up first the measurement on the bit number 0 and bring it down to, let us say, the bit number, sorry, into the classical register 0. Okay, so how do I do that? To do that, remember, I need to bring them down from the plus minus down into the 0 1. So that is the reason why I apply the so-called uh, gates out over there. And I, before I just run the simulation, what I will do is I just draw the circuit, right? So let me first execute this. The outcome has already been there because I just wrote this yesterday. And let me just run this. And if I run this, you will see the output coming up here. Yeah, right. So this is the so-called output here. Okay, so I've taken the I gates and then also applied the Hadmards, and then this will ensure the fact that are now brought back into the ket 0, ket 1, and that is what I am going to actually do the measurement out over here. So if at all I run this once again on my simulator, so this is my simulator instance which I'm setting up, and I'm setting up something like 1024 shots, and I can get the counts and then display the specific values in the counts, and that is what I'm doing. Let me run this part, and if you just run this, I'm not displaying the histogram, you can also do that. If you look at that, I just get the bit value C0 which I'm trying to monitor, that gives me a value equal to 0, and that 0 indicating the fact that this is the constant. And the same thing, you can also fire it. This I'm not executing right now, so I can just pick up a bunch of backends, try to find out which is the least busy backend, and uh, pick that up and then push the job, execute that onto that particular backend and wait for the results. And once I get the results, I can typically once again display the outcome there. So I'm not firing this job. Okay. I think Prakash, you are there.
Yeah, I'm
Hello?
there.
Yeah,
Yeah, I'm
Prakash?
there.
Yeah. See, I think what I will do is now the next part I just quickly cover in the next session in the first 15 minutes. That is basically how we can just create a oracle, right? So oracle
Okay.
function because it's already at 8:30, so I don't want to run beyond that time.
Okay.
Yeah.
So we can stop here
Yeah.
and close the part one we have covered, and part two we'll cover next. Is that okay with everyone? Anybody has any questions before we close?
Okay, I'm going to share all of them, Prakash. I'll just share these codes. Also, the earlier ones,
Mhm.
also, I'm going to share all of them into the respective folders, right? So
Correct.
maybe give me a day or two, and then by probably Wednesday. So today is your Monday, right? Yeah, by Wednesday, all these codes, all the samples which you have been discussing will be in the respective folders. So participants can extract from there, and then they can also try out with these workbooks.
So anybody, Tuma, Thomas, anything you want?
Thank you. No?
Yeah, I think once again, there's a
Okay.
quick question from Jimmy. He says that there's a Hadamard gate. What is the purpose of the Hadamard gate in step number three? So the Hadamard gate is typically required to once again take the measurements in the 0, 1 states. Right, our measurements are all in 0, 1. So currently our operations are in plus minus. So I need to move them back. Remember, we had the inputs in plus minus, sorry, in 0, 1. Use the Hadamard, move them over using superposition, move them to plus minus, operate it out there, and once again back from plus minus, moving down to 0, 1. We use the Hadamard gate in step number three. Yeah.
So I will simplify it that normal standard basis is 0 on basis, and for any superposition normally we put a C naught to make sure that there is a superposition. Even Hadamard can be used for superposition, but Hadamard is usually used for inputs as well as outputs to measure, so that we can always get it uh, z or plus or minus is equal to 1 by root 2 of ket 0 plus or minus ket 1, and so it transfers that into a measurable 0, 1 basis. So standard basis we are able to measure. So whatever may be the result, if you want to bring it to 0, 1 basis, so Hadamard of Hadamard gives you the same thing. So if you have something x, some input 1 or 0, you do a Hadamard and then you reapply Hadamard, you will get back the same thing. And so it's a transformation which is uh, for conversion, for mapping from the plus minus basis to 0, 1 basis, and vice versa. Anything more? Any questions? Yeah, I think you have some links asked, and I think yeah, the YouTube link is provided there, which is https colon www.youtube.com/at OpenTech Forum 1140. I think that is available. And John, thank you for that. And anybody who wants to subscribe can subscribe to it. All the 12 sessions are there, and so that would be helpful to everyone. Plus, you also have the drive which I had put in the beginning, saying that we are having Google Drive, which has all the information. So if you go at the beginning, there is a Google Drive specified, and you can use that Google Drive too, which is https colon drive.google.com/drive folders slash 163p IJUULW and some THX TZMIYA and some more numbers. I think it would be better if you can copy paste it. All sessions are available on YouTube, as well as slides are available in those Google Drive. So you can cover up to session 12, and if there are some plus minus, we have put some people, some of them, it could be forward backward, but essentially we have tried to cover everything, and the prescribed book which is there is what you use if you have any questions on the solutions, problems and solutions. Hopefully this will give you a good uh, informal as well as formal, because we have also added the references and all that which you can use. Hopefully that gives you. And if anybody has any questions, last call, please. There is a new message. Okay, what was that message? Okay, what is the purpose Hadamard gate? That we have answered, right? Any other? Is there anybody any questions? If not, Gokhale, can we close? Gokhale? Looks like Gokhale is dropped out. Okay, I think we'll stop the session here. Okay, thanks everyone. See you next week. Again,
Thank you.
thanks, Mr. Yeah, thanks everyone.